Next, so I was looking at these graphs here. Look at this graph. If you try to draw this, you're okay. But here you will have to lift your pen and then start to draw there. Same thing here. You can draw here, that's okay. But to continue to the right hand side, you'll have to lift your pen once to get that dot, and then again to continue from infinity going down. Let's try the next one. You're drawing from the left. You're fine so far. But as you approach this point, you have to lift your pen, come to this point, lift again, and go there. Here, you draw, lift, draw, lift, draw, lift, and so on. So you see, these are various kinds of discontinuities. This is called a removable discontinuity. All you need is a point to plug in that hole and you're continuous. So that's a removable discontinuity. This is an infinite discontinuity. There is, you are going to infinity here. This is also an example of removable discontinuity. All you need to do is plug in that hole. That is, move this here and you are continuous. This is called jump discontinuity. Okay, jump discontinuity. So, removable, infinite and jump discontinuities. These are the three kinds of discontinuities. Here is another definition. A function is continuous from the right at a number a if the right hand limit is equal to the value. Function is continuous from the left at a if the left hand limit is equal to the value. A function f is continuous on an interval if it is continuous at every number in the interval. If f is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left. Okay, so right hand continuity, limit x approaching a at right equals value at a. Left hand continuity, limit x approaching a from the left of fx is value at a. Okay, what does this mean? On an interval, you say on an interval, you have to be continuous at every point in that interval. What happens at the endpoints? At the endpoints of your interval, you have to choose either right or left continuities. Okay. Here are some important results, theorems. If f and g are continuous at a number a and c is a constant, then the sum of continuous functions is continuous. The difference of continuous functions is continuous. Continuous function times a constant number is continuous. Product of continuous functions is continuous. Quotient of continuous functions is continuous as long as the denominator is not 0 at your chosen number. All right. So quotient you have to worry about because you don't want the denominator to be 0. All right. Now, here, polynomial function is continuous everywhere. Polynomial is continuous at every number in the real number line. Rational function. Rational means polynomial over polynomial. It is continuous wherever it is defined. That is, the rational function is continuous on its domain. All right. Here is volume of a sphere. Volume is a polynomial function. R being the radius. 4 by 3 pi r cubed. Volume is a continuous function. A ball thrown vertically into the air with velocity. Look at that. Height is 50t minus 16t squared. This function, notice it is a polynomial. So it is a polynomial function, therefore continuous. Most functions that we are familiar with. Okay. cosine theta, sine theta. They are trigonometric functions. They are continuous. Okay, in fact, continuous on their domain, but cosine and sine are continuous everywhere. All right. Limit theta going to 0 of cosine theta is 1. Plug it in. Limit theta going to 0 sine theta is 0. Plug it in. Tan is sine over x. Well, this is quotient of continuous functions. So tan has to be continuous except when the denominator goes to 0. Okay, so look at tan. Denominator goes to 0 at pi over 2, 3 pi over 2, 5 pi over 2, so on. Negative pi over 2, negative 3 pi over 2. So all those points on those numbers, it has infinite discontinuities. Otherwise, tan is quite continuous. So all the discontinuities tan function has are infinite discontinuities. Okay. So the following types of functions are continuous at every number on their domain: polynomials, root functions, rational functions, trigonometric functions. Okay. So these are continuous at every number in their domain. Domain, it's important. Okay. Now, here is about composition, the composite. If f is continuous at b, so you see f composed g as x approaches a. Well, as x approaches a, we always, when we look for composition, we compute inside first. Then g, limit x approaching a of gx is b. So you now want to look for f at b. Limit x approaching a, f of g of x is f of limit. So you see, f being continuous at b allows me to take the limit inside. Okay, that's an important result. This is not typeset very well, but the point is f composed g is continuous at a as long as the limit x approaching a is going to give me f at b. All right. So composition of continuous functions is continuous as long as we have the correct numbers in place. Okay. Now I will start on intermediate value theorem in the next video.